Hey, and welcome to 8.4. This is going to be a short secondary video that's going to accompany the main lesson. We're going to take the skills and ideas that we learned in the main lesson and see how they apply to real life. So let's go ahead and let's get started. Okay, so I've created two problems of which we're going to have to use this idea on. The first one, it looks like we're going to build a circular pen for livestock and we need fence wood. You decide that you want to split the pen into three sections. The first section takes 50% of the area. The second section takes 20%, and the third section takes 30%. If the pen has a radius of 40 meters, calculate the following: the outside length of the first section, the outside length of the second section, the perimeter of the third section, and what is the length of fence wood you'll need for the entire 3-pen circle. Okay, so I think the best idea when we look at this is let's draw a quick sketch to see what we're working with. So we have a circular pen for livestock. And if I have a nice circular pen, I know the first one takes half the area. So I'm going to go ahead and cut the circle directly in half. The second one takes 20% and 30%. So I'm going to split this just off center. And we have a radius of 40 meters. So I'm going to go ahead and list that. So there's the center of my pen. Looks like I've got a big section, small, and a slightly bigger one. And so part A asks us to calculate the outside length of the first section. So basically all this is this is going to be an arc length problem. If I want to find the outside length of the first section, all I want to do is I want to find out what is this. And so we know the fact that if it's 50%, half of a circle, I know that my theta is going to be 180 degrees. That's half my circle. And I know my radius is going to be 40. So I'm going to plug that information in to what we've been working on. So I know that a full circle is 2 pi r times whatever fraction of the circle we're looking at. So out of 360 degrees, I'm only dealing with 180. So if I plug in my information, 2 pi times 40, I'm dealing with 1/2 of that regular circle, which means as I work my way across, 2 pi times 40 is 80 pi divided by 2. This is going to be 40 pi, or the equivalent to so it's going to be 40 pi, or the equivalent of 126 meters. And so that's the length of the first section. The length of the outside length of the second section, well, the second section, let's take a look, was the 20% one. So it's going to be this one right here. Okay, so we want to find that length. Well, now this one I'm going to need to do a little bit of an extra step. Instead of half of a circle, I'm looking for 20% of a circle. So I'm going to have to figure out what 20% of 360 is. So all I'm going to do is multiply 360 times 0.2. And what I'm going to get is that's roughly 72 degrees. Not percent, 72 degrees. Ignore that. 72 degrees. So there's my theta. Another radius is going to be the same. The radius is still equal to 40. So let's go ahead and let's plug that information in the same way that we just did. If I have 2 pi r times 72 of my full circle, I know that I'm going to get 2 pi times 40 of 72 over 360. And so if I work all that out on the top, I'm going to get 5760 times pi divided by 360, which is roughly 16 pi, or 50 meters. And so I've got 126 and I've got 50. And so that concludes A. Now we're going to move over to B. And now B asks a slightly different question. It wants the perimeter of the third section. So not only does it want the outside edge, it wants the inside edges as well. which means that we're just going to have to do arc length again, because how long is this section? Well, 40, which means if this is also a radius, this is also 40. So I'm just going to find the length of this arc and then add 40 and 40. So I'm going to add 80 to that total. So let's go ahead and let's take a look at how that would be found out. So for part B, I'm going to say, hey, I need to first figure out my theta. And okay, so I've got to figure out it's 30% of 360. So if I multiply 360 times 0.3, I get a theta of 108 degrees. Not percent, we're not going to make that mistake again. 108 degrees. So let's go ahead and let's plug that in. So we have a 2 pi r times 108 over 360, which means 2 pi times 40 times 108 over 360. So again, this would be the full circle, but I'm only dealing with part of the circle. So if I work all that out and multiply 2 times 40 times 108, that'll give me 8,640 divided by 360, which is going to be roughly 24 pi, which is 75 meters. Now, be careful here, because most people, once they realize they're finding arc length, they're going to stop right here, because that's how the first problem was solved. But let's not forget to add our 2 radii in. So I'm going to have to add 40 and 40, which is going to bring my grand total, so my perimeter is equal to 75 plus 40 plus 40, or 155 meters. Awesome. Okay. Now let's scroll up. What is the length of the fence wood you'll need for the entire 3-pen circle? Well, I know what this length is now. I know what this length is, and I know what this length is. So I could add up my values of arc length, and arc length, and add up 1, 2, 3 radii. Or let's say the problem didn't ask for these, and I'm just looking at this completely outside the box. I'm like, hey, I want to find the length. All I need to do is find the circumference of the circle, which means that I'm going to need to figure out, for C, I need to find the circumference and then add the inside fencing. Okay. So the circumference of a circle is 2 pi r, which is 2 pi times the radius of 40, or just 80 pi. And the inside fencing was, we had 3 sections of 40, which is going to be roughly 120. So what is 80 pi plus 120? Well, 80 pi, we're going to find that out to be roughly 251 plus 120, which is going to bring our grand total to 371 meters. Yeah, we're using meters. Awesome. The alternative would be I could add 150, 126, and 75, and I would get the 251. And then I'd still have to add the 120, which would bring us back to 371. Okay, so now the second question that we're going to be looking at is the Earth has a diameter of 12,742 kilometers, and the ISS is orbiting 408 kilometers above that surface. So if after 75 minutes the ISS is orbited 292 degrees, how far did it travel? And what's the orbital speed? Well, like always, let's go ahead and let's draw a diagram to see what exactly we're looking at. So let's go ahead and let's take a look at this slightly misshapen Earth. This is Earth. And we know it has a diameter of 12,742. And we know the ISS is orbiting 408 kilometers above that. So I'm not necessarily going to draw this to scale, but let's go ahead and let's draw a dotted line above the Earth's surface. And we're going to assume this is the ISS. And we know that distance right there, that distance is going to be 408. So Now, the reason why I drew the diameter out here is this isn't necessarily going to be useful. Most of the time, diameter, we're just going to list it in terms of radius. So half that 12,742 is going to be 6,371. That's my radius. So let's see what the problem is asking us. So part A. If after 75 minutes the ISS is orbited at 292 degrees, how far did it travel? Well, that's literally just asking us, okay, in this case, if I went around 292 degrees, how far did it travel? That looks like an arc length. So let's go ahead and let's figure that out. Our theta must be 292. And our radius is 6,371 plus the 408. Now, why are we adding the 408? Well, we're traveling. Is the ISS traveling at the ground? No, it's traveling in space. So we have to add that little 408 to the radius to get the true radius. So our radius in this case is actually 6,779. And we're just going to plug that in just like we'd plug anything in. So we would say, hey, our full circle would be 2 pi r times the percentage of the circle, or the fraction of the circle that we've orbited, which is 292 out of 360. So it hasn't quite gone around once yet. So 2 pi times 6,779 times 292 out of 360. If I multiply everything across the top, I'll get something like, let's see, I'm going to write this over here. Let's see, that's going to be 3,958, 936 pi over 360, which is roughly equivalent to 34,548.2 kilometers. So it's traveled pretty far. And the second part of the question was it wants to know, what is its orbital speed? Well, that's a pretty easy setup to do. Basically, what we're going to do is we're going to say, hey, if it traveled 34,548.2 kilometers in 75 minutes, well, what would that speed be in 60 minutes? So kilometers per hour. And we just solve that. So let's see what we'll get. Cross multiply. 75x. 60 times 34,548.2. That's going to give me, let's see, 2,072,894, and it's got some decimals. We're going to round that for right now. If I divide both sides by 75, it's going to cancel that. So my speed is going to end up being roughly 27,639 kilometers per hour. So there's my answer to A. So my answer to B is going to be almost the same setup, except for instead of degrees, it looks like they gave me radians and they gave me a different time frame. But regardless, the setup is going to be the same. So for part B, we know the fact that the ISS has orbited a total of 6.11 radians, and it wants us to tell you how far it's traveled. So how far has that orbit gone? Okay. Well, we know that our theta is 6.11 radians, and we know the radius, again, is just like before. We're going to take the Earth's radius and we're going to add in the orbital distance, which is going to be 6,779. And then we just plug it in. So we'll get 2 pi r times 6.11. Now, are we dividing by 360? No, we're going to be dividing by 2 pi this time, because if we remember, a full circle in radians is 2 pi. So we get 2 pi times 6,779 times 6.11 over 2 pi. We notice that I have a 2 pi up top and on bottom, so I'm literally just multiplying these two values together. So I get 6779 times 6.11, which will give me 41,419.7 kilometers. Awesome. And so now let's see, what is that speed in kilometers per hour? Well, I know it traveled 419.7 kilometers in 90 minutes. So how fast would that be in 60 minutes to give me a kilometers per hour? So let's cross multiply. 90x, if I multiply 60 times 41,000, we'll get, let's see, that's 2,485,181, and there's some decimals, but we're going to round in this case. Divide that all by 90. And when I say round, I want you to realize that I'm rounding my writing. I'm leaving the answer in the calculator, so the calculator is going to keep all these decimals. So our final answer isn't rounded. But for the sake of writing, I don't want to write out decimals all the way to the end of the paper. I'm just going to write out the whole number equivalent. And when I divide this, that number divided by 90 is going to give us 27,613.1 kilometers per hour. Hey, so we notice the fact that our answer from part A and part B is almost the same, which is good because that tells us that if we did have a rounding error, we're getting about the same speed. Now, if you got a speed right here and you got something very, very different, that would tell you that maybe we messed up somewhere, or maybe something's happened, like it's decreased its speed and it wants to drop orbit, or it's increased its speed and it wants to go to a higher orbit. But regardless, if you get two drastically different answers right here, something's going on. And so let's go ahead and let's check. What is the land speed for the ISS? Well, let's take a second and think about what it's asking us. Well, we figured out our orbital speed, which tells us how fast we're moving around this outer circle. The land speed is it wants us to tell how fast we're moving around this inner circle. So we're going to have to use one of these setups, but instead of using the adjusted radius, we're going to have to take back off that orbital distance. I'm going to have to take back off that 408 kilometers. So just because I'm biased and I like radians, because it does this nifty 2 pi's cancel out, I'm going to use part B as my model for part C. I'm going to say it traveled a distance of 6.11 radians, and its radius was the original radius of the Earth because we're using land speed, so 6,371 kilometers. And so let's figure out what that is. So we need to figure out the distance traveled, so 2 pi r times the 6.11 over 2 pi. The full circle times whatever fraction we're getting. So 2 pi times 6,371, 6.11 divided by 2 pi. I notice that my 2 pi's cancel out, which means it's just 6,371 times 6.11, which is going to give me roughly 38,926.8 kilometers. And I'm going to use that to set up my final proportion of if it did 38,926.8 in 90 minutes, how far did it travel in 60? What is its speed per hour? So I have 90x, I multiply these two, and I'll get 2,335,608.6. And again, the calculator is storing many more decimal places. I'm rounding this for the ease of my writing. X equals 25,951.2 kilometers per hour. And now if we notice that, if you were trying to stay beneath the ISS, you would have to travel almost 2,000 kilometers per hour slower than the ISS is traveling. So those are two examples of modeling arc length given some sort of real life scenario. So you can see the problems aren't really too terribly complex as long as you just figure out, hey, if I have a whole circle, what portion of that circle do I need to find information on? If you have any other further questions, let me know.